Thank you so much, Don. It's so wonderful to be back here in Alaska, where you have the trifecta of everything. You have aurora research, you have aurora in the sky, you have an amazing community of aurora photographers and enthusiasts here as well. So all things aurora are here. I'm excited to be back here and to tell you about our project. Okay, so I'm going to start at the beginning here and also, acknowledge my folks who are here. They'd never seen aurora, so we decided this was the time. And also, they also inspired my love for the natural world and scientific things as well. But want to start there with, that's kind of how I got interested in science, but really that grew in college. But before it grew, I really actually became almost weeded out of physics and never would have continued in physics had I not had a wonderful mentor at the University of Washington, and I had a NASA Space Grant Scholarship there that sponsored that research, and I became involved in aurora research there, and that sounded cool. It sounded like physicists were actually doing something that was useful and interesting. And then also in college, I was really fortunate to do a research experiences for undergraduates program here in Fairbanks at the Geophysical Institute with professors Tom Hallinan and Hans Nielsen. And that was really cool to continue researching, learning about pulsating aurora, learning about optical data of aurora, putting that together with rocket data of a pulsating aurora flight that was led by the University of Washington. And so it was really a great experience, and we also got to do lots of things around the state as well. Then in graduate school, I continued and went on to work on these hardware experiments that fly on the rockets above the aurora. And I worked on little particle detectors that fly on rockets, in this case from Poker Flat. So I came back and was part of a number of rocket campaigns here. And that was also really great training. The rocket program is really great training for hands-on experimental physics students. And this was actually the last time I was in Poker Flat. But some things have changed, some things have not changed. So I put some vintage pictures from that rocket campaign. And some of my now colleagues in the audience will recognize some others in our field from that as well. And so what being part of a rocket campaign as a graduate student allowed me to do was then to work on another aspect of understanding how the aurora are born and evolve. And in this case, going further out into space, into the Earth's magnetic field region, and working on same kind of experiments, but with a larger satellite platform. And so I worked on teams that build particle instruments. You can see a couple of them here for DOE and NASA satellites. And so I did that at Los Alamos. We, just like for a rocket, you test everything beforehand, but for a satellite, you do it even more so. And that was really great as well. And now, before I continue here, you know a little bit about me. I'd like to learn a little bit about you. So starting with, could you raise your hand if you have not seen aurora? Okay, how many people have seen aurora thousands of times here? Almost everybody. This is so cool. I don't normally get to talk to this kind of audience. So I'm not gonna, go through that much of all the aurora basics that probably most of you have heard of. But interestingly, in my field of heliophysics, many of the scientists have not actually seen aurora with their eyes. And so they study the data, they study the models, but they do not come up here or other places, and they don't actually experience it for themselves. So that's That's interesting. And how many of you are familiar with the term citizen science? Wow, this is such a great audience. There's so much going on in terms of community science, whether it's auroras or environmental phenomena here in Alaska. So that's also really good. And how many of you have done citizen science with auroras? A couple people. Then I can encourage you all to, after this talk, work with us on our project and tell you about why we are doing this. And so the reason we're doing this is that in 2011, I had a new idea about how everyday people could help us study aurora. And I actually got on a website called Twitter, which is all kinds of breaking news and these tiny little tidbits of information. And there was a really large geomagnetic storm in October of 2011, and it was really well timed for darkness on the whole eastern seaboard of the United States. And it also was primarily red, which is very unusual and occurs higher up in altitude, so it can be seen much farther south. And in this case, I got on Twitter and I noticed that people were reporting they were seeing the lights, and just with time, it kept going further and further south, all the way down to Alabama. And yeah, and so the idea was to put those observations on a map and to build a system that would regularly collect that kind of information. And then I began to learn about citizen science, which is a process in which the people can engage in the scientific process, asking questions, collecting data, and interpreting the results. And so we built a system for this specifically, because if I also ask how many of you are not on Twitter, how many of you are not on Twitter? Yeah, I was thinking you might not be, but you have a website and we now have all kinds of smartphones, and so you can use aurorasaurus.org and you can go directly to the website and be a citizen scientist there. And citizen science, I highly recommend this book or Karen Cooper's new book about citizen science and stories of the way that people are changing the way we do science now. And it's also a way, another author quote, it's about falling in love with the world more. And when you study something as beautiful as aurora, it's important not to lose that. And so this project has really helped us connect the bridge between the sort of science world where we look at data and try and figure out this complex phenomena, and people who are engaged and who really love the aurora for many, many different reasons, and where we can collaborate. So that's really been awesome. If any folks want to get more involved in citizen science for any topic, there's a great website called sighsstarter. That's kind of the clearinghouse. You can enter, what age or range you're looking for, or type, or location, or region, and they have all kinds of suggestions for you. So that's a really good project website to check out. And there's also, a NASA project called GLOBE that Elena Sparrow and others here at the University of Alaska are working with NASA on, and all over collecting observations of the natural world and collaborating on Earth science. So that's another one with NASA satellites and Earth science that's a really cool connection and has existed for a long time and has all kinds of great outcomes. And so there's also an app for that if you like to observe clouds, and that's a good gateway to staying up all night for aurora as well. So how do aurora occur? I'm going to go over this kind of stuff pretty quickly since you all have seen it thousands of times. But basically, the sun gives us energy all the time, not just light, but a continuously varying stream of charged particles of plasma. And that plasma interacts with the Earth's protective magnetic field. I have to kind of use my hands here, so if the sun is in the back and that plasma is entering the Earth's magnetic field region, it's being convected all the way around into the night side and then coming back towards Earth. And that's why we have auroras that peak near midnight. So in that way, the Earth's magnetic field is like an obstacle in a stream, and the solar wind and all of that is streaming around us. But we have all kinds of complex interactions in our magnetosphere that cause aurora, including as the Earth's magnetic field responds to solar particles, it collects that energy and stretches the magnetic field on the side where you have, on the dark side of the Earth, and then it can explosively release and come back towards Earth. When you see that, that's when the aurora is really lighting up over the whole sky. The aurora also varies so much from all of this. This little cartoon does not help us that much. Because it's this complex 3D process. So another thing is that satellites are really expensive, and so it's difficult to monitor this huge region from the sun to the Earth. It's 93 million miles. And we're watching what's happening on the sun and this constantly varying stream, but there are some important parameters, such as the constantly varying magnetic field environment that's going to interact with the Earth's magnetic field, that we cannot sense remotely. And so we don't know that until about 1 hour before that solar wind stream hits the Earth's magnetosphere. And when it does that, we'll get a good idea of how strong the aurora are and where they're going to be visible. But until you get within a couple of, until you really can sense that plasma, you can't accurately say aurora is going to be right here, right now, and this form. So it's a very big challenge, and in terms of space weather forecasting. And now that we have smartphones, that's one way to help us get a better alert of where the aurora are really active. If you're really wanting to find out, is it here, or is it over Fort Yukon, or is it in Anchorage, or where's it going to be? And then as well, when the magnetic field stretches, there's particles tied to the Earth's magnetic field, and they have all kinds of complex motions. When they rain down on the upper atmosphere, they hit the gases of the upper atmosphere, excite them, and release light. And so that's the color that you see at the very upper edge. There's not much oxygen, and you get a little bit of red light. Mostly at these latitudes, you see a lot of the green. And then the particles that are raining down, they're kind of losing energy with each collision. And unless they're really active, they're not going to get to the color below the green, which is kind of a cool pink color when they hit nitrogen molecules. This is a cartoon, not so good of portrayal of aurora, but you've all seen it, so you know what I'm talking about, hopefully. Okay, so this is important because we do not have global imaging of auroras all the time. We have a very extensive ground-based network, but there can be clouds on the ground, and you can't see all over the place. And then we also do not have we have pretty coarse models of where the aurora should be. So in the past, we've had satellites looking at where the aurora are, and hopefully we will in the near future. But in the meantime, there are different threats on Earth from the currents associated with aurora, and there's also a whole variety of magnitudes of activity the sun could give us. And so it's important to monitor that and as well for that reason. So enter citizen science opportunity. And in this case, this is this one busy slide of all the things Aurorasaurus does. Primarily, if you go to the website, there's a map with a bunch of different kinds of reports. Those reports can include photos. We've published a number of papers about the results, and over the last 6 years or so have had more than 7,000 users and reports, and opened that data up with this platform as well. So how it works is that you can go to the website, and we're just asking for a report of, did you see the aurora, yes or no? There are some pretty simple questions there. And then there's different types of reports, whether it was yes or no, whether there was a tweet. We also pick up these tweets that people are tweeting all over the place. I've seen tweets from the weatherman in Nome about aurora, and our system picks up tweets all the time. And so those are useful as well. Mostly, I don't know about mostly, but we've, over the last solar maximum, where the aurora are more frequent and the auroral oval is larger, this is a snapshot from one day where there were a number of reports across the US-Canadian border. And so mostly where I am talking about and talking to, there are people who are interested in seeing aurora in the northern states and don't know how often they actually can see it. We also have a simple plot, if you hit the plot icon on our website, of something called the Akasofu epsilon parameter, which is a simplified parameter that goes up when activity goes up and takes into account all the solar wind parameters you need to worry about, which are the magnetic field magnitude and direction and the solar wind velocity as well. All those things can vary in different directions, and that is can be a challenge to interpret, although many people have already taught themselves how to interpret lots of space weather data. This was an attempt to make it a little bit easier and to color code like what those levels are with a scale that goes up to thousands of gigawatts and really large input here. And way up here in Alaska, you don't need that much to really get great aurora. So way down here at the green line kind of bar, you can have great aurora here. Okay, so it's useful for people to help us basically verify and ground truth this model and build a better model. That's one of the main goals of the project. This is kind of the form that you fill out. When and where you saw the aurora is the critical information. Because here on Earth, we're always, the Earth is rotating, we're rotating under the auroral oval, and especially if it was early in the night or if it was after midnight, that information, you're typically going to get different types of aurora. We have other questions about those types. Was it like a discrete arc, or was it patchy, pulsating aurora? There are many different types, and we've, in our question, we only ask about 3 types that are most easily distinguishable, but you can also provide more information about what you saw as well. How active it was, that's also really important to know, because it can be really active for just a few moments as well sometimes. If you like Twitter or want to help with finding those tweets that are real-time reports of aurora, we actually need your help, because we have built a system that pulls these bits of text, and those bits of text have some locations with them, but it's really hard for the computer to identify, has the person said, I just want to see aurora in Fairbanks, or I just did see aurora in Fairbanks. And so you can go to the website and you can upvote or downvote those tweets as well. All of this system was built to operate automatically, to be robust to a large storm when you're really going to have thousands of reports in a short amount of time, and to have a database that is accessible to people. One of our early results during a large storm in 2015, the St. Patrick's Day storm, showed that people are actually seeing aurora quite a bit farther south of the anticipated model prediction of where they could see aurora. And that model prediction comes from the NOAA Space Weather Prediction Center. And in our case, we've utilized people's reports to give a better, a more accurate estimation of where people can see aurora. That's of course changing rapidly as well. It's kind of a qualitative assessment because cameras are getting better and better, and sensitivity is changing as well. Another thing to note is that this model and the solar wind monitoring, there aren't public models that in real time predict when you're going to get the peaks of activity and when the aurora is going to explode over the sky. And so that's something that people can report, and our whole system very quickly can alert people if they've seen aurora, and the aurora has come a lot farther south very rapidly. Okay, so that sort of regular cycle of energy storage and release that happens every day, every couple hours here in Fairbanks, has a lot of variability. The aurora is not a well-behaved thing because of all this constantly changing input, but a very smart graduate student, Shinaka Sofu, in the late 50s and 60s, discovered that there is actually a pattern to this energy storage and release, and described it in a substorm cycle. And I've kind of put some words to that here as well, in terms of not how the scientists would describe it, but how you might see it here and what you could look for to identify where the arcs are likely to start. Are they going to come towards you? Are they going to come south? And when are they going to start to be more active? And in addition to coming towards you, moving south or moving towards the pole, are they also moving east and west? All of that kind of stuff is in the science, but is not often communicated that well. So this is just a very crude attempt to start describing that. And I was putting this together because I was last week at a great place in the Northwest Territories with people who'd never seen aurora and wanted to help them spot it as well. And these were some of the patterns I was noticing. And these are all cell phone camera pictures as well. I'm not a photographer, so I was just using my relatively new cell phone. That's another technology innovation, is that just in the last couple years, like 2 years, cell phones can take these pictures also. So in addition to helping us build a better model, the photographers and citizen scientists are noticing when the aurora does really interesting things. In this case, this is an image that I originally saw on Twitter. It's a person from Saskatoon, and they were walking to their normal aurora spot, and they stopped and snapped this photo because there were these regular beads all over the whole sky, and they thought, that might be kind of interesting. And indeed, there are researchers interested in this kind of pattern. It only lasts a couple minutes. It indicates instabilities, and we want to look more at this. And also there's a difference in resolution between people's cameras who are outside looking at the aurora and the scientific mode of cameras, which are set up to be robustly collecting data all the time. So they really complement each other as well. Another kind of opportunity with citizen science data is something called Steve. And Steve is not just Elena's husband, but a really great story about an unusual, not typical aurora that the citizen scientists in the Alberta region and others as well were noticing. And it wasn't something that had a thorough scientific explanation. We went to the literature, we tried to find what this was, and could not find a thorough description with all of the information that the photos were showing. And this is a movie. Sorry, you cannot see it too well, but there's basically like this strange purple color arc, and it's overhead at latitudes like Calgary, while the aurora is far to the north. And so people started seeing this, and they started taking more and more observations. Just one photo of this, probably the aurora scientists wouldn't have taken much notice of it, but when they keep asking questions and when we don't have explanations and keep taking observations, this is when it got really interesting.
And they started noticing something that was overhead.
Sorry. Okay. Oh. Ooh.
It was unlike most aurora. Talked to the scientists who didn't know what it was, and together.
I wish you could hear this as well, because I really now know what editing does, and it makes me sound really coherent and describe this, but the sound's not quite working, so I can talk along to my own video here. But you see this narrow arc, and then there's also these green fingers of what we call picket fence, and this had really not been described at these lower latitudes. And so we started taking more observations along with the University of Calgary and others. There were satellite observations of an instrumented satellite cutting through one of these arcs. And so we found an event that had multiple people reporting this. It had clear skies at some of the University of Calgary sites, and it had data from the SWARM European Space Agency satellite. And what that showed us was actually allowed us to understand this is not your typical aurora. This is something that's actually been seen by satellite images, satellite data for a long time as a really strong flow and a really strong heating of the particles. And basically this is a very narrow east-west arc overhead, and the satellites are going north-south, so they're cutting through this thing. And when they cut through this flow, they measure, boop, here's the really strong flow, here's a really strong heating of the charged particles, the electrons in this region, and there's not much density at these lower latitudes. And this kind of thing had actually been studied for 40 years and is called a SubAuroral Ion Drift, but was never known to be visible. And so, and certainly not known to have these other features, these transient green features along with it. And so it's really been exciting to document that this is an extreme subauroral ion drift, and there have been many more people studying this as well. And however, I'm not sure what the right conjunction is there, but as well, Steve is not new. So this is a very recently published paper reminding people that we've rediscovered some old observations of Steve that we did not know about when we published the paper in 2018. And these observations are pre-space age. They are taken by Carlstormer and his colleagues in Norway. And in this case, he was a scientist, amazing aurora scientist from 100 years ago who had a whole network of observations across Norway, was one of the first to, actually, I think the first to measure the height of aurora with multiple sites, and his cameras and his people all over Norway were connected by telephone lines and coordinating observations. They were out for decades, and he took something like 12,000 aurora photographs from multiple sites and established the height of aurora from that. On 7 days, he saw something called Steve, and he took some photos as well. This is one of his pictures from a publication in 1933. This is a photo from 2017. They look quite similar in terms of this is what it looks like just kind of going over the horizon or over the house here. And notably, he noticed that the spectra, the color, was not your typical auroral color. And he because he was so good at getting the height of aurora, he really noticed that these are not the usual altitude of aurora. So he called them feeble homogeneous arcs of great altitude. And this was rediscovered, as it were, by someone who's on the non-professional space scientist side, amateur professional, or you could call him a citizen scientist, but someone who's an aurora historian from Germany, a man named Michael Hunekel. And he read the original Steve paper, and he said he was familiar with aurora history, and he went back and he meticulously went through all kinds of archives of older aurora observations looking for something like this, and he's found a lot of those. So you can read this paper that just came out today for some of those references as well. And there's also really great and still unexplained physics along with the picket fence. This is kind of a sped up video from a local undergraduate student, Andy, who's in the audience back there. Wonderful photographer, and has also contributed these kinds of observations as well. And this video shows a number of unique aspects. Okay, now I know you're all about to get on Twitter. You can follow Steve. This is run by the Alberta group. They're really fun, and they share a lot of news about Steve, which there has been a lot. This is another great image of Steve from the Alberta area. Okay, the Steve story has gone viral a couple of times, and that has really helped both recruit and reward citizen scientists with our project and with the Alberta Aurora Chasers. In my last few minutes here, I want to kind of shift to another mode of citizen science, another story that is evolving and exciting. And this is what I call extreme citizen rocket science. And this is an expedition that's going on right now in Norway. Two women, one of whom I'm taking a picture with here, are on by themselves in a trapper's cabin 100 kilometers from the town, the farthest north town in the world, on the islands of Svalbard. And they've been out there for about 6 months. Their expedition is raising awareness of climate change, and they're doing citizen science. They're doing like 10 different citizen science projects along with their time there. And though auroras do not really have to do with climate change, because they're in such a dark place, they can see some very special auroras. So they're contributing to Aurorasaurus and even contributing to some rocket science that the University of Alaska, Mark Condi, and others here, Don, and students here are involved with as well. So in this case, basically, they're kind of back in the mode of Carlstormer, and this is actually, they're only connected by satellite phone. This is a recreation of that sort of image, and they were so excited to be part of a rocket campaign. And what happened was they got dropped off with all of their supplies south of, this is kind of a blow up of Svalbard. They're well south of the town, but they happen to be at a very advantageous point for a rocket campaign that was going on in December. There were several rockets being launched from both north of them and south of them in Norway. And this was all to study this special kind of aurora that only happens when it's dark at noon that far north. And that kind of aurora is called Cusp Aurora. It's caused by the solar wind directly impacting the atmosphere, and so that makes it a special type of aurora, different colors. And these rockets also contained mechanisms to create their own artificial light and trace otherwise invisible aspects of the neutral particles that also are occurring in the upper atmosphere. And so this isn't the exact video from the rocket flight, but this kind of unusual sight was happening from their rocket. They stood by for 2 weeks at least, waiting for the call that they should put on all their gear, go outside in the total darkness, set up multiple cameras, look for polar bears, and take shots of aurora. And they happily did it. And also the scientists were happy that they had a potential additional ground site. This is a low-res version of one of their images. This is the only one I've seen yet. All the other ones are stuck in the ice with them still. But hope to get those in a couple months and work with people here that these could maybe additionally help understand the 4D structure of these neutral particles and how they're moving along with this cusp aurora. Okay, so if you would like to learn more about that or any of these kind of stories, aurora science, you can definitely check out our blog. If there are any kids, there are a couple of unique recommendations for kids to learn more about this. There's a great podcast called Wow in the World. They did a really super episode on the Steve Aurora, super creative, super fun. Adults should listen to it too, actually. And then we recently did a classroom webinar about Aurorasaurus, auroras, and with this Hearts in the Ice expedition. They also have a website and a blog about these two women, how they're surviving, what they're thinking about during this time. It's really great as well. And then over the last couple of years, we've done several blog posts on students that have been interested, whether it's a student whose science fair project is on Steve and on aspects that are actually not yet described in the literature, or a high school student who's a NASA intern and wants to build a small satellite to study Steve. There have been a lot of cool activities, and there's also opportunities while I'm up here. We're starting to collaborate more with the university and with serving folks here and students here as well. So the original project was not built for students, but we want to include students as well, for sure. And especially here, because you can see aurora, there's good opportunities for that. For adults, if you want to learn more, we are showing a Canadian-made movie about Steve that's really heartwarming tomorrow at the university. We have other activities as well. We have opportunities to be what we call Aurorasaurus ambassadors, who are local leaders. Typically, they may have their own groups or expertise, and collaborating together with scientists, doing outreach, and learning more together. And that's our ambassador opportunity. And then there are also really great groups in the Fairbanks area that are encouraging and keen to learn more about aurora science. So that's been exciting to connect more with those groups as well. For the researchers in the audience, I know, it's after 7 here, but we do have lots of papers about Steve and Aurorasaurus and this work. Citizen science is being encouraged in the heliophysics decadal survey, decadal process, which is going on now, about what the priorities in the field are, and also being encouraged at NASA as well. So happy to talk more about that. And the future is bright. These are some of our ambassadors, and we're excited to do more citizen science, more with satellite auroral imaging, and excited for the next solar maximum in a couple years with even newer cell phones. So I will end there, so I have a few moments for questions, and thank you all very much.
Thank you.